Welcome everyone to today's seminar. Our speaker is Dr. David Bjerklie from the United States Geological Survey in East Hartford. So David Bjerklie did his undergraduate studies in marine biology at University of Maine in Orono, and then he did his master's degree and PhD at University of New Hampshire in Durham in hydrology. And so David has done very interesting work in modeling the hydrogeology of coastal Connecticut, including the important problem of the possible effect of sea level rise on groundwater. And he has also worked on estimating river discharge using satellite data. But more recently, he did a very elaborate study about the impact of climate change on the hydrology of Long Island Sound, and that is what he will speak of today. So let us welcome David here.
Thank you, Sultan. So yeah, today I'm going to talk about a model that we developed for the Connecticut River Basin, but it also included the Thames River and the Housatonic River. So it covered quite an area, basically most of Connecticut's in the model, and a good portion of Vermont and New Hampshire. We did this modeling work as part of a larger set of models that were done across the U.S. By the USGS to look at climate change. And so I'll just go right into this. First, I just thought I'd introduce a little bit about U.S. Geological Survey. If you don't know much about us, we're kind of an agency that a lot of people don't know much about. They think of our topographic maps, but our largest, our largest component of the agency is dealing with water resources, groundwater, river flows, various elements of natural water systems in the United States. Of course, we also look at mineral resources, and we have a biological division as well. This is basically just what I just said. This is a repeat of that. And basically, the USGS, its mission is to develop data sets and to do studies that allow effective management of water resources, mineral resources, and biological resources in the United States. We're part of the Department of the Interior. So I'm just going to go now. This is just bringing right back to my original slide. So one of the other things I'm going to talk about, I'm going to show you the modeling we did, some of the climate, future climate conditions that the model simulated, but also I'm going to link it to some issues of water quality. But the first part of this modeling exercise, we did a small model for a small watershed in Connecticut called the Temperautre River. And the larger model we did was based on this smaller model, and that's what I have here. The goals of our modeling was to be able to really understand spatial and temporal variability of hydrologic processes and hydrologic variables. Really to look at specific water resource management issues. In the model I'm going to present here, the large one for the Connecticut River Basin, our specific things we looked at were snow and groundwater. But in the small model we based the larger model on, we had a whole host of issues we were interested in, including land use change. But one of the key objectives was to develop a GIS-based model, meaning we could build a model and parameterize the model completely out of GIS databases. So we wouldn't have to spend a lot of time actually doing a lot of calibration, because the data was coming straight out of available information. So that was our goal. And by doing that on the small model, we then were able to go to the larger model without having to spend a lot of time with each, given that the Connecticut River has a large spatial extent and actually a lot of different diverse environments as you go from Long Island Sound all the way up to Canada, different climatic kind of environments. We didn't have to try to calibrate each individual element of the model separately, because we wanted this to be derived completely out of the GIS. So this is the small model we did. It was relatively, it consisted, this watershed touches on 8 different towns. The model that we use is called PRMS, Precipitation Runoff Modeling System. It's a USGS model that's publicly available online. If anyone wants to look at this model, all the documentation is online, it's all free. But basically the model takes a watershed or any sort of hydrologic unit, and this can be, you can set this model up any way you want. It can be gridded, you can set it up by different land use types, land cover types, soil types. I set these up by sub-watershed because it's a lot easier at that to do it that way, to add your information up, to come up with stream flows and so forth. But the model is flexible enough to use any kind of hydrologic unit you want to model. But what it does is it breaks the unit up into a surface runoff component, subsurface, and a groundwater baseflow component. And so all the climatic exchange is occurring on this upper surface runoff layer of the model. So that's where the soil layer, soil exchange occurs, tree roots, precipitation. It's all happening right here. Anything that doesn't get removed by evapotranspiration, here there's actually some routines here that allow soil water to move directly into the groundwater reservoir or horizontally out. But anything that's not kept in storage in the soil here will either get transferred to the subsurface zone directly to base flow or out in the stream flow. So anyway, then the subsurface zone you can think of as the interflow zone. I don't know how many of you have had hydrologic modeling experience, but typically, you know, there's this zone often called the interflow zone, and it's beneath the root layer, and so exchange is not, there isn't any interaction with vegetation. So movement of water through this zone is controlled by structures in the subsurface, for example, clay layers or hard pan, anything like that. And if you're working in a northern environment, you could even simulate permafrost in that zone. But anything that gets, so in this zone, things can continue on vertically or horizontally out, directly into stream flow, or ultimately down as recharge into the groundwater layer. Now the groundwater layer is simulated in the model with a simple kind of a reservoir function. So it's, but I didn't do that in this model, but there's actually a new USGS model built on this that has brought in a gridded, physically based groundwater model and attached it to these upper layers. So there's actually a much more physically complete model available now in the USGS called GS Flow. I didn't use that here. The groundwater model it's linked to is ModFlow, and that's a gridded model. It took a lot of effort to link these two because they really operate on different scales. But anyway, so this is kind of the output we got from the small model. This was of interest to the towns where this watershed model is constructed. So right here I'm just showing groundwater recharge, and the blue being greater recharge, yellow. So what we could do then is spatially look at groundwater recharge across the watershed and also look at it seasonally. And that was one of the goals of that first project. Now, so we built From that small model, we scaled it up to look at the entire Connecticut River, the Housatonic River, and the Thames River. Now, this is a large 10,000 square mile area that we then modeled. One thing I'm going to do here to just point out, at the end, we like I said, we were interested in snow and groundwater recharge, but I'm going to discuss some water quality implications of the use of the model. You know, how the model might start looking at water quality issues.
I just have a sort of a naive questions, and I don't know much about this.
Okay. So your model actually sort of predicts groundwater recharges. So are there observations to validate those?
We do. We do have observations. But it's not that extensive. So the model is mostly calibrated on stream flow. So the output of the model. So that's how we generally calibrate. But you can calibrate at any level in those hydrologic. It computes, you know, evapotranspiration, soil moisture. It'll compute the recharge, snow. It computes snowpack. So you could calibrate at any one of those if you had enough data to do it. I have on this model. I have a paper which I'll give that link to anyone that wants to look at that paper. I have a copy here you can look at. I did compare, although we looked at a comparison primarily with stream flow, I also looked at available snow, available groundwater recharge information we had to look at how well the model did. So that's you can see that in the paper. But we broke the whole region into 511 these hydrologic response units. That's what you call in the model, the subregions. And we based that on a Huck 12 watershed. I don't know how many of you know about the Huck system, but it's a nationwide system that breaks up the entire landscape into small watersheds. Huck, and they have different, there's a Huck 1 through 14 actually for the whole United States. Huck 12, they tend to be about 20 square miles on average each. They're sub-watersheds. The Huck 14 is smaller than that, and the larger ones are the Huck 1s. And, the GIS information we used to build the model was information about the superficial geology and the bedrock geology, particularly the core stratified drifts. These are the glacial deposits that have filled valleys throughout New England. They tend to be the area of greatest groundwater exchange. So we look at geology basically to look at those zones versus areas of lower groundwater exchange, bedrock and till. We also have land, we look at land cover characteristics, forest type, also soils, we included in that. Impervious surface, we look at soils to characterize them, whether they're sandy, loamy, but one of the key elements of the model was to look at these Class D soils, which are, that's a classification from the Soil Service, or the NRCS, and it really is low permeability, clayey type soils that might support wetlands. Topography and slope and drainage density, which is the stream network, and that's really an indication of how fast water gets out of watersheds. So this is just a nice picture to illustrate that we're really looking at snow and groundwater recharge. That's Mount Washington. It's just a really great picture. Okay, this is the watershed then we looked at. And I have a pointer here. So what you're seeing in different colors are Huck 8 watersheds. These are the larger ones. But we actually broke this out. There's a bunch of smaller ones in each one of those. There's 511 sub-watersheds in that modeled area right here. All these points are the weather stations that we use to generate our input. So we have a regional network of weather stations. And I don't show on here the stream gauges we used to compare the model output, but there we looked at about 70 USGS stream gauges throughout this region. The other thing we did was we wanted to include the drought of the early 60s into our modeling. So we restricted our weather stations and our river outflow network to those gauges or those weather stations that had data going back at least to 1960 and spanning all the way up to the present. So there are probably in certain periods of time, particularly in the 80s, we might have been able to have a much denser network. But if we restrict to that long time period, this is pretty much what you get. There was about 70 weather stations we could use, and just coincidentally about 70 river stations.
So the meteorological input includes precipitation, temperature, water vapor?
No, we don't use water vapor. Yes, the input to the model is daily precipitation, daily maximum and minimum air temperature. That's all the model needs to run.
How about humidity? No.
The model will doesn't compute humidity because it doesn't deal with the atmosphere. But it predicts the evapotranspiration, which is controlled in part by humidity. So the routine that it uses is the vapor pressure. Now, there are a lot of assumptions in this model, but the model can use vapor pressure as an input. Typically, though, it's easier to use relative humidity. And so that can be an input to the model. And that would improve all your evapotranspiration estimates. I didn't do that here, but because there aren't that many stations where you can get that data. But it would be a great, and I know now you can get gridded products. I think some of them include relative humidity. And that would greatly improve this kind of a model to have that. But when we ran this model about 3 or 4 years ago, and we didn't use it at that time. But that's a good question or a good comment, because that would be a great improvement on that. We could use better routines to estimate evapotranspiration. Now this is just the output of the model. What you have here is the mean annual flow for the 49-year record we used for the 70 rivers that I said we looked at. And you can see that we had some problems down in smaller rivers. This is a discharge, the simulated discharge versus the observed discharge in the rivers, mean annual for the period of record. So we really deviated off this line in some of the smaller watersheds. And there's the reasons for that are two. There are two. One is we don't capture a lot of stuff that's going on in local watersheds, particularly if there's a lot of diversions in or out of the watershed, but also there may be local factors that are going on that our GIS representation didn't really capture. The other issue is because we have 70 weather stations and the model distributes that information across that whole region, because we used our routine for distributing the information used a kind of a linear regression model, X, Y, Z coordinates, to distribute information, precip temperatures, across to every one of those 511 response units. In the smaller basins, that distribution methodology can miss localized particular events, for example, heavy thunderstorms. So we will miss some of these events because of the scale and the scaling issues we had in the model. So consequently, I'm most interested in looking at annual and seasonal stream flows out of the model and not so much dailies. But anyway, that's why on some of these smaller ones we get the greatest deviation. But up in the larger ones, it did a really nice job. The model does a really nice job. Now this is just annual plot of total annual stream flow in the Connecticut River at Thompsonville, predicted by the model versus our USGS gauge. So you can see that interannual variability, I mean the year-to-year variability is captured pretty well by the model. And this is just the monthlies plotted, so you can see the kind of scatter plot we get on a monthly scale. This is a plot of the model predicted mean annual snowfall for the entire study area. So I just took as a lumped value by year. So the model what it can do is say, okay, how much snow fell over the entire region for each given year. You can see the wide scatter here. This is the just a smooth line through there, just so you can get a look at where. Particularly, I want you to look at this year, this peak around 1970. We'll come back to that. Now, what else we can do with the model? Because it's a distributed model, we can map variables. And so what I have shown here is on this side is just a map of the mean precipitation over the study period, 1960 to 2007, or 61 to 2007. That's just the map, what it looks like distributed. So you can see up in the White Mountains in New Hampshire, you get a lot more. In the Connecticut Valley, you get less, and along the shoreline compared to these highlands. So, you know, it makes sense. Now, what I'm showing over here is the trend surface of that data over that period of time. So 48 years or 40, whatever, I guess it was 47 years. Was there a trend in the data? And the blue color means there was a positive trend. So what this is showing that for this time period, precipitation increased everywhere in the basin, everywhere. There wasn't a single HRU that didn't show an increase in precip. And the darker the color, the higher, the stronger the trend. And that, so you can see in the highlands of Connecticut and from Massachusetts, you see the greatest trends. And there's fewer trends up in northern New Hampshire. But now, if you remove the drought of the early 60s, you can see that at the 0.05 probability level, all those trends disappeared. So, and what's interesting, if I change the probability level to a lower probability, let's say 0.1 or 0.2, they would all come back. But the reason I do this is to show you how much certain these meteorological events really, really affect your trends. And that was a severe drought. That was the worst drought on record in New England. So it has a big effect on how you interpret your trends. And of course, the other thing that has a big effect is the probability level that you're willing to accept, right? So this is maximum daily temperature. This is the distribution. Nothing surprising here. You have decreasing temperatures moving up to Canada. Now the trends on this are interesting as well. Maximum dailies have changed the greatest in southern Connecticut along the shoreline. And those trends continue even if you remove that drought. But if you remove the drought, the maximum temperatures have not seen the same level of change as they have down here. So what's going on here is, in my opinion, is that climate change is showing a much greater effect already in southern New England, and so it's kind of this threshold kind of a thing going on, and you might call it a gradient to the north. So we're experiencing change much greater in the southern parts of New England right now. minimum daily temperature. Same kind of a thing. Look at the banding here. Almost, you can almost put a line of latitude right through these. And so clearly the minimum temperatures are behaving very, very climatically, if you will, even more than the maximums. The trend is everywhere the same in the minimums. And even if you remove the drought, you still get a weaker trend, but everywhere throughout the region the same. So minimum temperatures are increasing faster than maximum temperatures.
What's the magnitude? Is this degrees per year or what is it?
This is mean annual temperature. Trend.
We can't see any of the numbers. What kind of size of those changes?
Well, this is the dark green. It's hard for me to read too. I have to get my paper out because I don't remember the actual numbers. It was a couple of degrees, I believe. So, okay, no, that was about a half a degree on the minimum.
Over the 40 years?
Yeah. Yeah. Half a degree C. So anyway, and then so also then now we can look at groundwater recharge distribution. This is just the mean recharge. This is the trend surface. So recharge is over the entire record is changing greater in the northern part, which is really a function of the fact that precip up here was increasing faster than evapotranspiration, meaning the inputs have exceeded the outputs, occurring faster in the northern part than in the southern part. Now, again, though, if you remove that drought, those trends in the groundwater recharge disappear. Snowfall, same thing. We can look at the very gradational distribution of snowfall in the area. The change, though, has been most observed in southeastern Connecticut and central Massachusetts. And that occurs irrespective of the data set you use. So even though we remove the drought, the same pattern, central Mass, southeastern Connecticut is where you've seen the greatest change in snowfall.
So this is just a point of clarification. So your snowfall is actually an output of the model rather than observation.
That's right. Yeah, these are the groundwater recharge and the snowfall are model outputs. Yeah.
How can the model calculate the snowfall by itself? I would think this would be an input, right?
No, it doesn't. It's temperature based. So it takes the temperatures as a routine, a snow modeling routine in the model. Now what I looked at here was I took this output of the model and plotted it for one of the HRUs in northern New Hampshire, the Ammonoosuc River. And so I just put a trend line through it. So this is the snowfall output. That's the trend line. And this is a fraction of total runoff. So how much of the total runoff came from snow? You see here, that's the trend. And again, I want you to note this peak at 1970. This is the same plot for a HRU in Connecticut. Again, we have kind of a peak in 1970 and a change. So something shifted. If you look at this plot, that one, and if we go back for the whole region, there was something shift occurred in 1970. And it goes, this is simulated information, but it comes right out of the temperature records and the rainfall records. Now this is a plot of actual stream flow measured throughout New England by the USGS, looking at the spring peak. In other words, the high flows in the spring. And what's interesting here is there's a shift, a real break in that curve right at 1970. So the real data plus the model data is all pointing to something going on around 1970, some kind of shift.
It shifts to earlier?
Earlier freshets, and that's coinciding with model outputs saying less cold, less snow. Yeah. Now this is the same work done by Hodgkins and Dudley. They're up in the USGS in our main office. This is a plot of a whole bunch of rivers in New England. This all behaving similarly, except for these which were actually sooner, around 1960. So, you know, it's pretty clear from actual data and plus our modeling data that 1970 is some kind of a threshold of something.
It's not 1970.
Are those some kind of running average or something? How are you getting those?
These are smooth plots. They're just
Are you
smoothing.
drawing it by eye or are you drawing?
No, this is a routine. It's a spline. It's a smoothing routine called spline.
So on a global basis, you see the recent warming trend started around 1970.
Either that or it reached some kind of critical threshold, at least in New England. Yeah.
Is the Hudson on there?
The Hudson, I don't think is on here. Now these papers, you can get the references for these papers. I don't think the Hudson is on here. These two guys, Hodgkins, Dudley, have done a series of them looking at lake ice. They've looked at, more recently they started looking at groundwater. They don't have anything published on that yet. So what I'm showing here is just, now I'm looking at the ratio of simulated groundwater to total runoff. And so in the upper region, the model simulation is showing that groundwater is comprising a larger part of the stream runoff, whereas in southern New England, it's steady or slightly declining. And this would have implications, of course, for fisheries, particularly cold water fisheries. I have an animation here. I don't know if it's going to work. I'll have. And this is, no, just it's fun to watch. Oh, it didn't work. I don't know how to activate it on here. So, usually you just hit that. No, it's not working. Oh. It's just a fun thing because you got all this output, you can animate it and you can see how things change. Kind of fun. So anyway, the next thing we did is we wanted to see, okay, we got this model, it's simulating things, it looks pretty good in many of the things it's simulating. So let's put in some global climatic change data. So we had access to all the various model outputs for these global models that were reported in the IPCC reports. I looked at 6 particular ones, and what I decided to do, because of limitations really of time and budget, I just picked the one that was kind of the median of all of these and ran it. And it turned out to the Bjerklie Center of Climate in Norway. Their model was kind of like the middle ground of all of these. They all had similar things, similar trends, with the exception of this one. The Russian model had tended to predict some things that were almost the opposite of some of the other models. But anyway, I just used this one, it's kind of in the middle, not because that's similar to my name. But my name is, I have a Norwegian name. I'm only, part Norwegian, but it's my name. I had to live with that. See, the Bjerklie. Anyway, so I chose that model. We developed output from it, and we essentially updated our input data sets with that output model, and then we were able to rerun the model. This is just some of my selection stuff when I was comparing the different models on different runoff and outputs. So anyway, so based on that Bjerklie model, the output fed into the model. This is what the change in snowfall is simulated to look like based on two different scenarios. And these are the IPCC scenarios, the low emission and the high emission scenarios. They actually have three scenarios. The low emission, you might be the good one, meaning we figure out how to control CO2 and so forth. The high emission is nothing changes. We just keep going the way we go. Now, unfortunately, on this, the scales aren't the same. So this is about 3 times amount of change is really predicted for the high emission. But what's interesting is where the big changes are occurring, depending on the two models. Both of them show a lot of change, the most change, in central Massachusetts, including here. And what that suggests to me, and less change down here and less change in the north, both of them. But it suggests to me that, again, because we're talking about snow, there's a threshold being reached. And down in Connecticut, that threshold is already in the process of being reached, where snow is declining. But in central Mass, this is where the action is going to be occurring in the next century in terms of reductions of snow. Groundwater, according to the high emission scenario, groundwater is actually recharged, meaning precip is outpacing evapotranspiration at a greater amount in the high emission scenario than in the low emission scenario. So groundwater recharge is increasing.
There's a question about these GCM outputs are sort of very coarse.
Yes.
Whereas in your calibration of the model, you use very fine observations to do that. So you redistribute the GCM data.
Yeah, and I know
based
there's
on your
there's a lot of different ways to incorporate and downscale these GCM data. And I know there's a lot of controversy about it. What we did here, and some people out in our research branch in Denver, were developed these input data sets for me and for some other studies with consultation with some people at NCAR. And they chose this route where they took the GCM grid and they just took the changes from that grid and applied it directly to the station data. So you might have a lot of argument with that to do it that way, but that's how our data sets were generated.
So it's basically uniform change in terms of temperature and precipitation.
Right. So it's just kind of like a scaled scaled change to every station. So we updated our station records. Now this modeling, a lot of the model stuff, again, using this model now, they're starting to rely more on the gridded data sets that are easier to downscale than station data. So now, today I would run this model with probably the gridded weather data. All right, so we have this output from the model, and so we can use this to start looking at other things that might be changing with climate also. So one thing that we tested here was to look at stream temperature, river temperatures, and ultimately to look at what might be coming into Long Island Sound. I know there's a lot of interest in this, particularly from fisheries. I know Janet and I actually we put together some concepts for a proposal that we submitted. We didn't get it, but we were looking at seeing how we could do this kind of thing on a large scale and look at how that correlates with fish distributions. So there's a lot of interest in this right now, and stream temperatures, river, predicting what might be going on in rivers and streams in terms of their temperature. And EPA has a lot of interest, a lot of the state agencies in New England have an interest. But anyway, so what I did was I just took, because the model tells me how much groundwater is coming in to the stream, how much surface runoff is coming into the stream, I could start saying, you know, those two elements carry very different temperature signatures. Groundwater is cooler, tends to be cooler, and more reflective of the mean annual air temperature. Surface runoff, it generally reflects the daily temperature of that day. So based on that, I developed a little routine where I could combine these two temperature signatures into a mixing model and predict the stream temperature. So I did that, and this is for the Shetucket River in Connecticut. The green is the simulated, and the blue is the measured at a station in the Shetucket. And this is for, I think, well, this is days on the bottom, but it was almost a 20-year period, I believe it was, or 15 or something. But at any rate, I put a trend line, just a linear trend line through that, and you can see that they both show positive trends. The means are a little different, and there's reasons for that. My application is fairly simplified, for one, but secondly, it all depends. This one, the simulation would predict some sort of mean temperature of the river based on the inputs. The blue is partly a function of where the stream temperature gauge is located in the river. So I didn't try to sort any of those complexities out. And you can see that the stream temperature will actually go down to 0 when it freezes over. But because I always have a groundwater input, I'm always going to have a little bit more than 0 in my simulation. Which actually makes sense because this river never completely freezes. So these going to 0 was really a function of the position of the temperature sensor in the river. So anyway, I didn't try to sort any of that out. I just was kind of looking at it. These are dailies plotted. So you can see, I mean, you can see that on a daily, you really can capture these broader trends and even get a lot of the variability on a daily scale with such a simple model. It's just a mixing model. So I think there's a lot of potential here when you think about source water, meaning where is the water coming from? What is its water quality signature? You can recombine them, and using models like this, you can actually start simulating some certain water quality aspects of the streams themselves.
Sorry, the axis on that top figure, for example, what's that the temperature of? What are we plotting?
That's the mean stream temperature.
Okay.
So the green is the simulated, the blue is our measured. And I just did a couple other ones for this small brook in Massachusetts. And then I could plot it. Again, the power of a distributed model, you can map these things. So this is the stream temperatures predicted in that way, mapped for different months. Now, the USGS is now working to link PRMS to an actual a complete stream reach temperature model. And that has actually been done now too. So this PRMS model now has been linked to a groundwater model, it's been linked to the stream reach temperature model. So these things are starting to become, and they're developing as even today, you know, these things develop every year, there's new things. So these are good models to access. They're all publicly available. This is just a diagram of that SNTemp model and how it interacts. The SNTemp model requires solar radiation as an input. PRMS will predict solar radiation. In many cases, particularly in arid regions, it does not do a good job, I don't think. So I think solar radiation is better as an input. Again, that's becoming more available, that data is becoming more available. So the other thing we can think of, I showed you temperature, but what about, we can look at nutrients kind of in the same way. This is just a schematic that we've developed kind of an idea of using these zones for water quality in Connecticut. And you can predict, each one of those zones has a particular nitrogen loading signature. And you can feed that into the stream flow output and predict nitrogen loading to Long Island Sound that way. So I didn't do that, but it's certainly, if we can identify a signature, we can do exactly what I did with temperature. So these are kind of things, you know, I'm interested and USGS is interested in doing more of, trying to link these things to water quality. And that's all I have today. Any questions?
I have two questions. One, I didn't quite understand what were the inputs. I know temperature was one of them. I was expecting wind would be one, since you are considered river transpiration. And the second question is in terms of comparison between, I know that the Connecticut River and the Shetucket are the major rivers here, and you did the Connecticut River and the other small brooks, but you didn't mention Shetucket. I would like to know how Shetucket would be affected by the climate change, if you did do it, but you did not mention it here.
Yeah, I can give you that data. You know, all those rivers we have the output for, I just didn't display it. One thing about the Shetucket, though, it's at its output, it's controlled by a couple of dams. So a lot of the output, it's not going to correlate with the observed because it's being held back in dams and so forth. But you can look at the simulation and what the simulation would say. On an annual basis, though, they don't hold back a lot of water. So on an annual basis, the Shetucket and the simulation do pretty well. It's just seasonal, and it's all highly affected by regulation. But I can get that data for you if you're interested. We can communicate by email. With regard to your question of wind. The model uses a Jensen-Hayes routine, which I compared it to various other routines, Penman-Monteith and so forth. On the scale, the spatial scale we're looking at, wind was not very significant. I know that wind is important in these equations, but they tend, when you apply them at a 20 square mile kind of a thing, the winds, at least in New England, didn't play a very big role. But all of that data, if we had that data, you could use Penman-Monteith in here to predict the potential ET. But without the data to support it, at all those weather stations, we really couldn't use it. So it's using a simplified, pretty simplified routine, the Jensen-Hayes. But Jensen-Hayes, it doesn't do relative humidity, but it actually predicts vapor pressure in New England is very, very, you can predict it from the minimum air temperature very accurately. And so the minimum air temperature and the vapor pressure are very closely related in New England. And it's not true in arid regions, but it is here. So it's not as bad as it might seem. Let's put it that way.
Bob, Alan?
So your model was tuned to sort of mean patterns of temperature, and I'm wondering how, given the role of episodic events like a hurricane going up the Connecticut River Valley, those would have huge impacts on the runoff and in particular the surface runoff. Is your modeling directed toward any of that kind of extreme event at all, or is it strictly the climatological?
Well, it uses daily inputs, so we'll capture some of that on the daily, but the really short-term ones, it's going to miss. But it will, in fact, during that time, some of those highs were Hurricane Floyd and some other ones that you could see in in increases in the runoff. But yeah, it's a daily scale time frame, and then I lumped it even further than that. That's where you were displaying it.
Peng Liu.
Yeah, so follow up about the seasonal difference. Bob just mentioned the summertime possibly hurricane. I would be interested in this cold season for the snowfall, because well, obviously there are different regions to control the precipitation during the seasons. So in terms of the consistent trend of both temperatures and recharge, so is there any seasonal difference if you consider the trend?
Well, no, but I haven't done a lot with this. After we prepared it, I haven't looked any deeper, really. I have not really looked much deeper. I haven't had the time or the budget to do it. Although I'd like to. I mean, there's tons of output from these models, and they can be looked at, and but I haven't, like the Shetucket, I've never pulled the actual data out to look at it.
Okay, so does the model calculate the soil temperature?
No.
Graded, then how is the river stream temperature calculated?
I calibrated it. And so what I did was, again, this is very simplistic. I said the groundwater input coming from the model, I gave it a temperature, characteristic temperature in it. One, it was partly controlled by the mean annual air temperature and partly controlled by the daily air temperature. And I just combined them until I got a good output. And you could do that. It was interesting because I did it for about 10 different rivers where we had stream temperature, and they all were quite similar in the way they balanced those two out. But again, it's a very complicated thing, and in fact, that I'm not really addressing in this. So I look at it as kind of a first cut way to look at stream temperature differences. But actual stream temperature, if I'm trying to predict that, I'd want to go to a model, a reach scale model like that SNTemp.
Yeah, so it looks like this can be coupled with the land surface model that calculates the soil moisture, soil temperature, and potentially say nutrients.
Yes.
Therefore, you have a better prediction of the water quality in the river stream.
Right. That's exactly right. That would be the next generation. Yes.
Yes, there is a question in the back.
Heat flux? No.
If you don't have repeats, then how do you get temperature?
Well, again, I just use the mean annual air temperature as my index.
So how, can you talk about how your snowfall is calculated? Snowfall.
Well, the routine that it uses for snow uses the daily maximum min temperatures as input. And there's, again, there are some things, there are some coefficients you tweak, like, for example, that address the heat capacity and so forth, but it's all a routine that is built into the model that you have control over, but it's really the only input it's using is the daily maximum minute air temperatures.
And so like the temperature is below 0 degrees, you say it's snow?
Yeah, but it's usually you set that threshold maybe at 34.
I see.
It depends. I know they use this model out west a lot, and they tend to have a higher threshold. I found that I just used 32 degrees, and that worked better here. But out in the Rockies, for some reason, the number is better to be about 34. I think because there's a greater temperature difference with elevation, so they use different lapse rates and so forth.
For many years ago, global models also use similar criteria. Yeah. So,
Well, I just wondered, did you try seeing how much skill your model had in predicting snow? I mean, you have observations.
I do, and it's in the paper, but I didn't present it here.
Is it decent?
It's very interesting. On a mean, you know what I did? Again, you're limited to how much snow data you have. But I used the MODIS snow cover. And if you take the MODIS snow cover and look at again, over the whole region, if you say how much snow cover does the model predict, how much snow cover did MODIS see? Very similar. But it changes. It way underpredicts in the north. MODIS shows less snow in the north. And MODIS shows more snow in the south than does the model. And I think, and there's a lot of things with MODIS issues coming in here. One is MODIS is seeing what's on the ground. So wind might have piled stuff up here and it looks like bare ground, but in fact, the model will say, if it snowed a ½ inch, the whole HRU is covered with ½ inch, right? It's not accounting for drifting snow. The other thing, so all those complexities come into it. And interesting because I think, I'm actually interested in writing a proposal and trying to get some work to do more with how do you take the model and how do you actually compare model output to observational things like MODIS snow cover? There's a lot of stuff to consider there, and I think that's something of interest to go forward with on future work.
Okay, so there are no more questions. Oh, there's a question.
There was one in the back.
Oh, I didn't see that.
Yeah, my question was
very
river flow, peak river flow, you can sort of say is when snowfall ends, and that's sort of backed up on the calendar a week or so. Can you also say anything about when snow cover begins? Is it beginning later in the year than it has historically?
I don't know if there's any observational data for that. There's, yeah, you know what? I don't know of any data for that you could use unless there are some stations that collect snow cover data, and that might work. A few stations will report snow from the co-op network, but I don't know if there's any comprehensive information on that.
Okay, so let us thank our speaker.